Hello friends, my name is Gaurav Naugare
And I am Ronak Rathod.
and today we are going to discuss about heterogeneous computing, its challenges and opportunities.
So now we'll start with the presentation.
Hello everyone, today we are going to explain to you about and we are going to discuss actually mainly about the heterogeneous computing challenges and opportunities. This paper has been published in IEEE Journal. The main author of this paper was Ashfaq A. Khokhar. It was published in 1993. My name is Gaurav Naugare and my friend's name is Ronak Rathod. So let's move on to the first one. Topic is our abstract of this paper. In this paper, mainly the heterogeneous computing style and the homogeneous computing style, they have been compared, and they're based on their comparison one brief summary is written in this paper, brief kind of review. And the heterogeneous, the advantages and disadvantages, mainly they have been focused on heterogeneous computing style, as it will be more of advantages and it will be taking over the homogeneous computing style in our future. So this comparison is based on some parameters like design issues, profiling and testing, benchmarking, etc., which has been discussed in this paper. So what is homogeneous computing? In homogeneous, it uses one or more type or more machines, but which are of the same type. The type of these machines will be same, but the whole process which we want to task or process which we want to get executed will be distributed over all of these machines. So as the amount of homogeneous parallelism in application decreases, homogeneous systems cannot offer the desired speedups. So that is the kind of advantages and disadvantage at the same time. So however, still there are numerous applications in our embedded systems also, where we still use this homogeneous computing. So moving on to the heterogeneous computing. What is heterogeneous computing? In heterogeneous computing, as I told you earlier, that as compared to homogeneous computing, there in heterogeneous computing also there will be more than one processors or computers, but they will be of different types. So an heterogeneous computing system includes I suppose means uh, nominally these heterogeneous machines, then some high-speed networks and operating systems, and they will be all combined to produce a compact positive impact on ease of use and performance. So during this time of 1993, this heterogeneous computing was a novel technique for solving computationally intensive problems that have been of several types of embedded parallelism. Now here, as you can see in the diagram, high-speed interconnection network is shown, which has been connecting all the processors like massively parallel processor, then image understanding architecture containing that processor, then Cray, which is is a very well known supercomputer. Then some user workstations are also there. They will be kind of small personal computers. Then connection machine is also there, and also this PASM, SIMD, MIMD machine is also there. As you can see, PASM means a partitionable single instruction multiple data, which is a mode in which all processors execute the same instruction synchronously on data stored in their local memory. So and MIMD is multiple instruction. M for multiple, S for single. So this in a multiple instruction, multiple data mode, the code stored in each processor's local memory is executed like independently as compared to single instruction, where the data stored in the local memory is executed on the same instruction synchronously. Now, how do you implement this heterogeneous computing? There are actually two approaches for implementing this SC paradigm. The first one, we will analyze the application where we can how we can use this application for how we can implement this application using heterogeneous computing. So for after analyzing this application, we will these researchers we will have to devise some new algorithms. They will have to come up with some new tech new like procedure, so how they can means actually uh, implement this application on SC computing style. So but in the second approach, we will have one existing parallel code of the application, which we may have run on the previous homogeneous computing style, but this time we will try to implement the same code on the heterogeneous computing environment. So if it doesn't run, so then we will have to make some changes accordingly, and we will have to run it again, like that. So uh, in the end, we will both approaches need some strategies for partitioning, mapping, scheduling, and synchronization. Now as we can see that diagrammatically, this first approach is the diagram is showing like user approach, uh, and the second one is showing the compiler approach. So in user approach, whatever be uh, the design of the program, first we will have been analyzed the design, then accordingly we will be planning the algorithm for it, and that algorithm will be mapped in this in this diagram. Like first it will be first that task will be there, then this algorithm our design, and then accordingly it will be partition and mapped, and then accordingly it will be distributed over the different types of computers, means heterogeneous computing style. So this one is the first approach, which is the user approach, and this one is the second approach, compiler style approach. In this compiler style approach, as we have mentioned, one existing code will be there. That existing code will automatically determine what will be the vector and what will be the MIMD processor the doing, and SIMD processor doing an SP, and then the partitioning and mapping will be done, and then accordingly it will be distributed among the different types of processors of heterogeneous computing style. That will be the compiler style. Then we will we are means we have faced some three issues as we are acting as a designer. So these three issues are as mentioned here. The types of machines available, which are the types of machines available in heterogeneous computing style, as heterogeneous computing style will be having different types of machines. Then we will be having some alternate solutions to the various sub problems of the application. After analyzing, we will get those sub problems, which are the sub problems, and of course we will get some alternate solutions. We will be having different types of solutions for a particular problem, and then for the cost will be also be there according to the types of solutions. The cost of the of performing this communication over the network will be different. So these three issues every designer should and must consider while designing the heterogeneous computing.
Hello friends, I am Ronak Rathod, and as my friend Gaurav explained you about the what is heterogeneous computing, what is homogeneous computing, and the issues in which he explained about the two approaches. Now I am going to explain you about the classification of HC computations. So first we'll look at the meta computing. Computations in this class fall into the category of coarse grained. So the instructions which belong to the particular class of parallelism are grouped to form a module, and these modules are executed on a suitable parallel machine. So this metacomputing refers to such heterogeneity at the module level. And now we'll look at the mixed mode computing. In this where we have in the metacomputing we are coarse grained, here we are having this fine grained heterogeneity. So this is almost alternate parallel instructions belong to different class of parallel computation. So this type of heterogeneity is not suitable for execution on the suite of heterogeneous machines because this communication overheads due to frequent exchange of information between machines can become a bottleneck. So if too many machines try to send a message, then this the data path will be uh, too much data will be there, so it will be like a bottleneck situation. So however, these programs can be executed efficiently on a single machine, such as partitionable SIMD or MIMD, which incorporates heterogeneous modes of computation. So this mixed mode computing refers to heterogeneity at the instruction level. So if we take an example, means for example, uh, we can use its mode switching capability to support SIMD, or MIMD parallelism and hardware barrier synchronization, thus improving its performance over a machine operating in SIMD or MMID mode only. So now we'll look at the code type profiling. So this program profiling involves testing a program assumed to be a consist of several modules by executing it on a suitable test data. This profiler monitors the execution of the program and gathers statistics, including the execution time of each program. So the fast parallel execution of the code in heterogeneous computing environment requires identifying and profiling the embedded parallelism. So what it used to be, this traditional program profiling involves testing a program assumed to consist of several modules by executing it on a suitable test data. So what the profiler will do means the profiler monitors the execution of the program, and it will gather the statistics including the execution time of each program module. Then this information is then used to modify the modules to improve the overall execution time. So in HC, the profiling is done not only to estimate the code's execution time on a particular machine, but it will also analyze the code type. So this is achieved by code type profiling. Now we'll look at the testing. So first we'll go for analytical benchmarking. Analytical benchmarking, it ranks the available machines in terms of their efficiency in executing a given code type. So basically this test measures how well the available machine performs on a given code type. So while code type profiling identifies the type of code. So thus analytical benchmarking technique permits researchers to determine the relative effectiveness of a given parallel machine on various types of computations. So this benchmarking is also an offline process and is more rigorous than the previous benchmarking techniques, which simply look at overall result of running an entire benchmark code on a processor. Uh, and note that the one thing that this analytical benchmarking results are used in partitioning and mapping. So now we'll look at the partitioning and mapping problems. So the partitioning problem can be divided into two sub-problems. The parallelism detection determines the parallelism present in the given program, and the clustering combines several operations into program module, thus partitions the application into several modules. These two sub-problems can be handled by the user, the compiler, or the machine at runtime. In HC, the parallelism detection is not the only objective. Code classification based on the type of parallelism is also required. This is accomplished by code type profiling, which also poses additional constraints on clustering. Now we'll go for mapping. The mapping problem can be defined as assigning problem modules to the processor so that the total execution to processors so that the total execution time is minimized. So mapping in HC can be performed conceptually at two levels, system and machine. So at the system level mapping, each module is assigned to one or more machines, and each module is assigned to one or more machines in the system so that the parallelism embedded in the module matches in the machine type. And in machine level mapping assigns portions of the module to individual processors in the machine. Now we'll go for scheduling. Scheduling in homogeneous environments, a scheduler assigns each program module to process to achieve desired performance in terms of the processor utilization and the throughput. So we have so many tasks to do it for a processor. So that task will be assigned based on the scheduling or the priority. So all the tasks are to be scheduled to get the proper throughput and the proper utilization of the processor. So basically there are three types of the scheduling. Uh, High level scheduling, which is also called the job scheduling. It selects a subset of all submitted jobs competing for the available resources. Another one is intermediate level scheduling. It responds to short-term fluctuations in the system by temporarily suspending and activating process to achieve smooth system operation. In this low-level scheduling, it determines the next ready process to be assigned to a processor for certain duration. So this low-level scheduling are not much of importance tasks, so they are given low scheduling. While all these three scheduling can reside in each machine in an HCI environment. So for this, we also need this fourth scheduling at the system level. This scheduler maintains a balanced system-wide workload by monitoring the progress of all program modules. So basically, this scheduling policies such as FIFO, round robin, shortest job first, and shortest remaining time can be employed at each level of scheduling. While while these communication bottlenecks and queuing delays incurred due to the heterogeneity of the hardware add constraints to the scheduler. So now we'll go for synchronization. So what is means this synchronization process? It provides a mechanism, to control execution, sequencing, and to supervise the interprocess cooperation. So basically, it refers to three distinct but the related problems. So there should be synchronization between the sender and the receiver of a message, specification and control of shared activities of cooperating process, and the serialization of concurrent processes to shared objects by multiple processes. So in this heterogeneous computing, this synchronization problem resembles that of distributed systems. So in both the cases, a global clock and the shared memory are unpredictable, and network delays and a variety of operating system and programming environments complicate the process. So what we are talking about is the correct choice depends on the topology, the reliability, speed, the bandwidth of the network, and in addition to these types, and also the number of machines in the environment. However, reducing this synchronization overhead is important to achieve this large speedups in HC, and this HC is more sensitive to synchronization overheads. The frequent handshaking for synchronization may expand most of the available network bandwidth. And now we'll go for this programming environments. A parallel programming language, parallel programming environment, by the way, includes this parallel languages, intelligent compilers, parallel debuggers, you know, syntax directed editors, and we can take configuration management tool and other programming aids. So in homogeneous computing, this intelligent compilers detect parallelism in sequential code, and it will be just translated into parallel machine code. And this HC requires this independent and portable programming languages and tools. So this requirement creates the need for designing cross-parallel compilers for all the machines in the environment, and this parallel debuggers for debugging cross-machine code. We have two different codes and we want to run on another machine. So for that, the code to be compiled in another machine, it's not supported. So we need cross compilers for that. So this heterogeneous computing offers new challenges and opportunities to several research communities. So for this to support this paradigm, we can research in some areas like designing tools to identify homogeneous parallelism in embedded application, designing communication protocols to reduce these cross overheads that occur when different machines communicate in the same environment. It can be developing standards for parallel interface between various machines, then designing efficient partitioning and mapping strategies to exploit this heterogeneous parallelism. And we can also go for this interface and user friendly programming environments, to program this diverse machine, and that too in the same environment. So indeed, this HC provides us and this opportunity to bring together research from various disciplines, and to develop a feasible approach for applications in the grand challenge in the problem set. So hope you understood the paper which we explained. So it's thank you from Ronak, and thank you from Gaurav also. Thanks for listening to us.